You clicked because you want to run open source models locally, but here is the hard truth. Model quality no longer matters as much as your graphics card choice. The real battle today is not about which algorithm is smarter. It is a hardware optimization war where your specific GPU determines if those clones can actually start running on your machine. By the end of this video, you will understand why parameter counts are lying to you and how to use new tools like llmfit to find models that fit your exact memory constraints without wasting money on expensive upgrades. For years, we operated under a simple assumption: more parameters equal better intelligence. If you wanted a smarter model, you bought the one with 10 billion weights instead of 7 million. That logic worked perfectly when everyone had access to massive server farms where VRAM was infinite and bandwidth was unlimited. But that era has ended. The open-source landscape is now flooded with over 100 clones for every major architecture, and they all demand different amounts of memory in ways that theoretical specs simply do not predict. Here is the thing you need to understand immediately. Marketing metrics like TOPS or raw compute power are becoming increasingly misleading predictors of real-world performance. A card might boast higher floating point operations per second than another, yet fail miserably when trying to load a specific quantized model because it lacks the necessary memory bandwidth for that architecture's KV cache requirements. The critical bottleneck has shifted from total compute capacity to VRAM size and speed. You can have the fastest processor in the world, but if you cannot fit the active weights of your chosen model into video memory along with the context window, the inference process grinds to a halt before it even begins. This shift forces us away from parameter count heuristics toward quantization-aware selection strategies. Tools like whichllm and llmfit have emerged specifically because manual calculation is no longer sufficient for this complexity. These platforms aggregate real-world benchmarks across hundreds of models to match specific VRAM constraints with actual performance data. They simulate token throughput and time to first token for mixture of expert architectures before you ever attempt a deployment. This automation reveals that theoretical capacity often leads developers astray, pushing them toward larger models they cannot actually run efficiently on their consumer hardware. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. Consider the case of an RTX 4090 with 24 gigabytes of video memory. You might assume this beast can handle anything in its price range without issue. However, data shows a surprising reversal where a smaller Qwen 3.6 model weighing only 27 billion parameters frequently outperforms larger alternatives in benchmark scores, despite having tighter memory margins. This happens because the quantization method used for that specific clone interacts more favorably with the tensor cores of your GPU than the unoptimized version of its bigger sibling. The architecture allows for better concurrency and lower latency, proving that raw size is no longer a proxy for capability when hardware limits are in play. Now consider this nuance regarding future efficiency gains. We cannot assume that matching VRAM to model size will remain the only path forward forever. Recent research into frameworks like Huawei's UG demonstrates that architectural changes can eventually transcend raw GPU selection alone. Their work on adaptive transitions from grouped query attention to multi-head latent attention has shown concurrency boosts of 2.69 times on NPUs compared to traditional setups. This suggests that software-level optimizations might one day allow older or less powerful hardware to run modern architectures with surprising efficiency, but we are not there yet for the average developer trying to deploy today. The current reality is defined by immediate VRAM bottlenecks and quantization fidelity rather than a universal hardware superiority. While community leaderboards aggregate data for consumer cards ranging from Apple M1 chips up through RTX 5090s, these resources lack standardized metrics for emerging enterprise accelerators or long-term thermal throttling effects under sustained inference loads. A card might run perfectly during a short benchmark test, but overheat and throttle within minutes of continuous generation, destroying your token throughput rates. This inconsistency means that hardware selection is now the primary gatekeeper for LLM adoption across all skill levels. Without matching GPU VRAM and bandwidth to the specific KV cache requirements of modern architectures, even high-quality models become unusable locally regardless of their parameter size or benchmark scores from other machines. You cannot simply download a model because it has a good reputation on Hugging Face if your memory architecture cannot support its active state during inference. This necessitates a shift where practitioners prioritize specific workload simulations over generalized buying guides until broader standardization emerges across diverse accelerator ecosystems. The race is no longer about training new architectures, but optimizing existing clones for local deployment, and the tool that ranks models based on recency-aware benchmarks against your specific hardware determines practical utility over theoretical model quality. The open-source inference landscape has fundamentally pivoted from a war of algorithmic innovation to a battle of resource allocation. We are seeing hundreds of versions of similar models competing not on intelligence, but on how efficiently they can squeeze into limited memory spaces using different quantization levels like 4-bit or 8-bit precision. The winner is the model that delivers acceptable quality while staying within your physical hardware limits, allowing for continuous generation without swapping to system RAM and killing performance. This realization changes everything about how you approach development as a junior engineer or hobbyist building production-grade applications locally. You must stop looking at parameter counts as the primary metric of value. Instead, treat VRAM capacity and memory bandwidth as your most critical design constraints before selecting any model for deployment. The tools that automate this matching process are not just convenient, they are essential infrastructure in an environment where a single wrong choice can render a powerful AI completely unusable on your machine. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.